Hi there. I'm Troy Warnick, and I'm here today with my associates, Nathan Johnson and Noah Clemens. We'd like to talk to you about fluidized bed technology and its applications in the petroleum industry. But first, what is a fluidized bed?
Good question, Troy. A fluidized bed uses a gas, like air, to help solid particles behave like a fluid. Now I know what you're thinking. Solid particles behaving like a fluid? Impossible. But how about a little demonstration to show this concept?
Alright, so using just a little bit of PVC and our handy dandy air compressor, we can easily transform this plain looking tub of sand into a miniature fluidized bed. Let me show you what I mean. So we've got here our sand, nice and sturdy. We got here a good piece of metal, probably steel, strong metal, dense metal. Put that right on the sand. That guy's not going anywhere. We could try to, we could push him down a bit, but he's not going anywhere because the sand is solid. But once we fluidize this bed, it disappears like a thief in the night. Not a trace. We turn back on, get our hand in there, try to find him. There he is. But
Now, what does this have to do with the petroleum industry? Well, what a lot of people don't know is that a lot of the components in petroleum, crude oil, are too heavy to use as commercial fuels like gasoline and diesel. Let me illustrate this with this diagram of an atmospheric distillation column, or topping tower, as they are commonly known in the petroleum industry. The column takes advantage of the fact that different components in the crude have different volatilities. The most volatile, or the lightest components, leave the column through the top. This cut contains light gases like methane, ethane, and propane. At various points along the side of the column, other components like naphtha, or unrefined gasoline, kerosene, diesel, etc., are drawn off as products.
The heavy cuts that come off the bottom of the topping tower are called gas oils, and they are too heavy to be used in gasoline and diesel blending. Let's take a look at the chemistry. Petroleum molecules are made up of hydrocarbon chains, long chain molecules made up of carbon and hydrogen. As you can see in the diagram, gas oil molecules are much longer than diesel and naphtha molecules. One of the primary purposes of oil refineries is to convert these gas oils into more valuable gasoline and diesel blending components by breaking up those long hydrocarbon chains.
one of the units commonly used at oil refineries to convert gas oil into lighter blending components is the fluidized catalytic cracker, or cat cracker for short. The cat cracker uses a zeolite catalyst to facilitate the chemical reaction that turns the gas oil into more valuable products. As any chemical engineer worth his desalter knows, you get the best results from your reactor when you maximize the surface area between your fluid and your catalyst. The cat cracker does this by making use of fluidized bed technology.
Let's take a look at how the cat cracker works. As you can see, there are three main parts to the cat cracker unit: a reactor, a catalyst regenerator, and a fractionator. In the reactor, gas oil is fed to the bottom of a riser. As it ascends through the riser, it mixes with fluidized catalyst from the regenerator, and the gas oil chains are broken. However, due to the high temperature and pressure inside the riser, much of the catalyst particles become coated with coke, a thick black covering which prevents the particles from doing their job. To remove the coke, the particles must be sent to the regenerator, where they are mixed with combustion air, and the coke is burned off of the particles, making them ready to be returned to the reactor. The products that come off of the top of the reactor are then sent to the separation column, where the valuable components are separated from the unreacted gas oil. because catalyst regeneration is exothermic, and the catalytic reaction is endothermic. This is a thermodynamically balanced process, where much of the heat generated in the regenerator is used to fuel the reaction in the riser.
Now I know what you're thinking. We've already got hydrocrackers and packed bed reactors. Why do we need fluid catalytic cracker? Well, let's take a look at some of the advantages of using the CAT cracker unit. All of this is made possible by fluidized bed technology that allows catalytic particles to behave as a fluid. They can easily be transferred from one unit to another. Fluidized bed technology is essential for modern oil refineries and other chemical processing plants.
Now, the first advantage is that fluidizing the bed provides mixing. See, when the catalyst gets fluidized, all the particles are free to move about and can mix really well. This lets us make the assumption that the reactor is well mixed, and every engineer knows it's a good day when we can make assumptions. Because of the mixing, the catalyst is evenly dispersed throughout the reactor, making the reactor more efficient than a packed bed reactor. In addition, the even concentration of catalyst across the reactor creates a uniform product that's hard to produce otherwise. Now, with the uniform distribution of catalyst comes a uniform distribution of heat. See, this makes heating or cooling the reactor a lot easier and a lot simpler. Because of this, it's a lot easier to reach and maintain the desired conditions for the reactor. And one final advantage of the catalytic cracker is that it can be run continuously, which is really important in the petroleum industry, since every minute not used making product is thousands of dollars down the toilet.
Well, folks, we've learned quite a bit about fluidized bed technology today, and its applications in fluidized catalytic cracking. Now I'd like to talk to our good friend Noah here, more about what makes fluidized bed technology work. Noah, why don't you tell us about your miniature bed that you engineered, designed, and created? What is it that makes that fluidized bed tick?
Well, it's a great question, Troy. I'd have to say there are really three keys, three main things that make a good fluidized bed. First, you need some good air pressure. That's where our air compressor comes in. That'll give us enough pressure to actually fluidize our bed. It's what gives those particles the energy to move around. The second thing is you need that air to be evenly dispersed throughout the base. Because you don't want hot spots and cold spots. You don't want some areas being kind of fluidized, right? So that's why we used a lot of small pieces of PVC, right? So we can get with, and in the PVC, there's a bunch of little holes that are evenly spaced, that are at 90-degree angles to each other in the PVC, so that way we get airflow going throughout the entire bed and not just one spot. Third thing, solid particles need to be really fine, right? The smaller the particles are, the easier it is to fluidize them.
So, I'm sorry.
Well, I was just going to say that's why we used sand, that's why we use the finest available sand that we can get our hands on. Because that is much, much easier to fluidize than coarse sand or gravel or something.
So Noah, what you're telling me is that would be a pretty bad idea to try to build a fluidized bed from bowling balls.
Yeah, that would be a bad idea. You'd need a lot of air pressure to fluidize those guys, and the result of that being a massive fluidized bed full of bowling balls, any one of those could fly out at you at any time and take you right out.
But it could be done.
Well, theoretically, yeah, it could be, if it had high enough air pressure.
Well, no, I guess my real question is, if you had enough air pressure, could you fluidize an entire planet?
I want that note you hit there.
Perfect.
Well, that was fascinating. Now let's take a closer look at fluidized bed technology and its applications in petroleum. Nathan, why don't you tell us about the first time that fluidized bed technology was used in an industrial application?
Well, Troy, I'm glad you asked. The first person to use fluidized bed technology in industrial application was Fritz Winkler, a German-born chemist from Zell, Maine in 1888. He used fluidized bed technology in coal gasification in 1922.
I see. Tell me more about coal gasification.
Well, coal gasification is a process in which syngas, a mixture of carbon monoxide, hydrogen, carbon dioxide, natural gas, and water vapor, is produced from coal.
I see. What do we use syngas for?
Syngas, or synthetic gas, is a fuel with many properties similar to natural gas.
I see. Now what role does fluidized bed technology play in the coal gasification process?
Well, you see, fluidized bed gasifiers fluidize fine dry coal to promote mixing between the coal particles, the oxidant stream, and the steam stream. The resulting mass transfer produces syngas.
Well, that's all well and good, Nathan. But now I'd like to know more about the petroleum industry. When did fluidized bed technology get introduced into that industry?
You sure do love petroleum, Troy.
I sure do. If it weren't for petroleum, we'd have no fuel for our tractors, combines, locomotives, and semi-trucks. We'd all starve and die.
That's true. Unless we all learn how to grow our own food. But to answer your question, Troy, one of the first United States fluidized bed reactors used in the petroleum industry was the catalytic cracking unit, created in Baton Rouge, Louisiana in 1942 by the Standard Oil Company of New Jersey.
Gee, Nathan, it sounds like fluid catalytic cracking has played a pretty important role in our nation's history.
I'll say, Troy.